Welcome to this short MedChemica MC Pairs training video. In this video, we are going to look at how we examine the outputs of a RuleDesign run that has been exported to Excel. We are going to illustrate how you can analyse and use some of the statistical data exported with the compound suggestions. We will assume that you have already done a RuleDesign run by inputting a molecule, setting your goal, for this particular search, increase in solubility, and set with advanced filters. For our search, we have an output of 107 suggested compounds. We use the save function to export an Excel spreadsheet, and once this is exported, for most browsers, this will appear down the bottom left-hand corner. Once downloaded, we can double-click on this to open this in Excel. So let's open this Excel spreadsheet. The first feature you will see is the compounds rendered in the fourth column, and where we have used the substructure lock, they should all be aligned in the same way. So you will see the hinge binder is towards the right. The first row of the results is the input compound that we suggested, with its physical properties calculated to get an idea of the baseline that we are starting from. After that, the compounds are sorted in increasing molecular weight. So we see the lowest molecular weight compound at the top here with 302 Daltons. The highlighting shows how much of the molecule overlaps with the input molecule, which is highlighted in yellow. So we are looking for the part where the chlorophenyl has changed, and in this instance, this is to a cyclopropyl. Another feature of the output sheet is the is known and compound name columns. If the compound structure is known in the central database, it will be true in the is known column, and we'll put the compound identifier in the compound name field. That is one of the first things we can filter on, so we can remove all the trues in this column. This is quite a useful feature, especially as a project advances. The tool will potentially suggest things that we have already made. The pair data column is a method of drilling further into the match pair data for the performed transformation to generate this suggested compound, and we will cover this in a separate training video. So there we go. This is the input structure compound suggestions in increasing molecular weight. To the right of this is a heat map of the base array of compounds and any of the goals that we have selected and their rule data. You will notice that there are hidden columns between these coloured columns. Where there is a value missing, it means we do not have any data or any rules for that given assay, for that given transformation. Where you do, you will see a coloured block. Green is good, red is bad, yellow is neutral, and blues are neds. No effect determined. What we suggest as a workflow is to scroll down the new structures and find a compound we like the look of. Once identified, we can then further explore the rule data by moving across the row. The column header is a fixed row, so we can easily refer back to what the data equates to. So let's go to the 4-cyano compound here. We can now scroll across this row and we can start to see a reasonable amount of green. Green for log D, green for the solubility assays, which we asked for. We will come back to the ned in a second. There's then more green for free fraction, and as we scroll our way across, we can see more ned data. And down the other end, efflux ratio increasing for MD, CK, NAV, 1.5 decreasing. That's a good thing, and we see that HERG is a ned as well. Okay, there are many good things for this particular compound, with quite a lot of neds. Now is the opportunity to look further at the stats data and how we can use some of this data to assess whether this is a good idea or if this is a probable effect we are going to see. To reveal this data, we have to unhide some of the columns. So we grab some of the columns here with the ned data that we want to look into, and I'll just grab the next assay too. Once this data is unhidden, we can see the rest of the stats columns, and we can see the names are built up of the assay and the stats data it equates to. In a previous training video, we described matched molecular pair analysis and how we select rules. Some of these fields should therefore be familiar. The count of the number of pairs, the count of the number going up and number going down, the median change, and the standard deviation are some of the common ones we use. For more advanced users, we provide additional stats in terms of standard error, binomial test, and there are also other useful things like what the environment size of the transformation is, that's its specificity, and the delta heavy atom change, which is another field which can be quite useful for sorting the data on. For our cyanide compound, here where we have a NED, in this particular case, where it is an increased rule for solubility, we have 100 pairs, 74 up and 26 down. Now, these numbers don't necessarily always add up. You might be thinking, why might that be the case? Well, we can have a matched pair and two values, but both values are out of range. We don't count these in the statistical analysis, so that is why number up and number down don't always add up to the number of n-qual or n-quant. Let's scroll across to this NED data, because this was interesting but wasn't firmly a rule. If we look at this, we have 5 matched pairs, and of those, all 5 of them are increasing solubility. So if you remember, it needed to take 6 pairs to get a rule. Well, all 5 that we have are increasing solubility. That's not quite a rule, but it's pretty good. The median change is 0.3 and the standard deviation is 0.34. So we can start to visualise that the distribution is shifted to the happy direction. So there is perhaps a good chance we might get nearly half a log unit improvement in solubility. So that is a really nice example of how we can use the data. Let's find another example. We will go across and see what we have for Herg. We will unhide the Herg data. So we can see here that we have 55 matched pairs, where 25 are up and 30 are down. This is really interesting as it's nearly a 50-50 split. We can also see that the median change is 0 and actually has a reasonably large standard deviation of 0.4. So it is just on the side of improving Herg, but with a 50-50 chance. We can now make the decision to see if that is really what we want to do. So maybe it isn't the best idea, although if we did get an improvement, we won't get as much as half a log unit probable change, which is a surprise for a group that actually reduces lipophilicity. So there we go. That gives you an idea of how we use the NED data and how we can do multiple parameter optimization. This has been a short video looking at the output data from a RuleDesign Excel exported sheet and looking at the stats data and how to use the stats data for NEDs to make an informed decision. If you require further support, please contact support@medchemica.com. Thank you.